Hello, honors physics students. Let's get started by going over some homework. We'll start in the textbook with the conceptual question number 6, which talks about two different light bulbs, each connected to the voltage of 120 volts. We want to know which bulb has the higher resistance, which bulb carries more current. And again, as I've mentioned, we have a lot of new vocabulary this topic and new units to really get used to. So, the more you can review that, the better off you're going to be. So we have the 120 volts. Of course, the volts is telling you that's going to be voltage. We got 25 watts or 100 watts. That's the capital W there. Remember, of course, that's going to be power. All right, so remember, we have three different power equations. I'll put them up here on the screen. P equals I delta V, P equals I squared R, P equals delta V squared of R. And as soon as we derive these three equations by combining the original power equation with Ohm's law, I gave you this helpful advice, which hopefully you're keeping in the back of your mind, that here's how we know which equation to pick. And here's the usefulness of it when we're comparing resistors, which is exactly what we're doing here in conceptual question number 6. All right, comparing resistors, we got to choose the equation that has some value that is the same. Here's where this comes into play. So we have these two light bulbs. Obviously, the power rating is different, 25 watts, 100 watts being a lot brighter. But what's the same? It's got to be that voltage, the 120 volts. So which equation is the one to choose? Well, hopefully you chose this third one, because it's the one that has something in common. That's the delta V. And the power is different, and we want to know something about their resistance. So really all we're doing is using this equation here. Now, can you go ahead and calculate? Of course you can, but really we shouldn't, right? We're at the honors level, we're late into the year, we know what to do. We look at the equation and we just sort of see the general relationships. We're looking for the one with the higher resistance. So we see resistance in the denominator here. So we say, if this is a large value, what does that do to P? Well, we're dividing the same delta V squared by a larger and larger resistance. Obviously, it makes the power less and less, right? And so in this case, the larger resistance, the one with the less power, that's going to be the 25 watt bulb. Yes, of course, you could just calculate and see it that way, but we always want to practice our algebraic skills. The second part is about which bulb carries more current, but it's the same deal here. We look at our power equations. We want to pick something that's the same. It's going to be the delta V, so it's going to be this first equation now. We have the same delta V, but different powers, and how does that affect the current? And here it's an even easier relationship with delta V being the same. If the current is the larger value, that means the power is the larger value as well, and so the larger current comes to the one with more power. That's going to be 100 watts, where again, you could just put numbers in and calculate, but we really want to be able to just look at the equations and see it just by inspection. Okay, now we flip over to our Cutnell and Johnson. We're going to take a look at problem number 5 here. And again, we are changing things with the power equations. As you know, since we've been doing this all year long, you know you're always looking at equations here. Alright, so we'll just take each of the three statements in turn and see which equation is best to look at and what happens. So this one, first statement is about voltage and current. So which equation should we be thinking about? Well, it's going to be this one, the first one, because it has voltage and current, right? No magic to this. Okay, so what do we do? We're doubling voltage and reducing the current by a factor 2. So here's how I express that, as we've been doing all year long. Double the voltage, current down by a factor of 2, or 1/2 the current. And, I mean, you can put numbers in if you'd like to, but you should just see from the algebraic statement here that 2 times 1/2 is the same. And so, yes, of course, the power is unchanged. We can put a check mark. Statement 1 works. We'll do the same thing for statement 2. We have voltage and resistance. So which equation are we looking at? Well, it's this one, because it has voltage and resistance. So we're going to double voltage, increase the resistance by a factor of 4. And so I know that you follow what my advice is all year long. I know, of course, being honor students, that you put your voltage and the factor in front in parentheses, because that's what I've been training you to do all year long. I'm sure you're making me proud in doing this, because now, of course, we see that the factor in front is also squared. So we have 2 squared on top. We have a 4 in the denominator. 4 over 4 is 1. It is, again, unchanged. So statement 2 works as well. Okay. Statement 3, we got current and resistance. Well, we only have one equation left. Obviously, we're using I squared R. We're doubling current. We're reducing the resistance by a factor of 4. That means it's a 2I in parentheses squared, because, again, I know that you honor students are doing me proud, and you're putting that in parentheses, right? So we know we square that too. This is 1/4 the resistance. Is the power unchanged? You bet it is, because here's a 2 squared, which is 4, times 1/4, which is back to 1. And so, yes, all three statements work. And so our correct answer here is choice A. All three of these keep the power the same. Fantastic. Okay, let's open up notes. And if this were a normal class, I would have you copy down this in your notes. And so I'd like you to do this. You're going to pause the video. You're going to copy all 6 of these circuit diagrams, these schematic drawings, into your notes, because this will give you good practice in drawing the circuit elements. All these circuits have a source of voltage. It's not indicating which is positive or negative, but remember, the long line is positive, the short line is negative, and they have these different resistors and different arrangements. Even the batteries are in slightly different arrangements, because you can draw the battery any way you want. Alright, so you're going to practice doing this, draw all of these nice and big in your notes, and then I want you to go through and identify each as either series, parallel, or compound. You can just write S for series, P for parallel, C for compound if you'd like to. Here I define compound as a combination of series and parallel. So really take your time with this, pause the video as you do so, come back and I'll go through the answers. Okay, so if we were in class like normal, the first thing I would ask you to do is identify which of these is plain old series. A through F, tell me a circuit that's just series, and a lot of students right away tell me that letter C is series. But then first thing I say is, wait a second, look at this. This resistor and wire, and this resistor and wire seem to be on parallel lines. Doesn't that make them parallel? Well, hopefully you remember from last class when doing the activities that there are different definitions for series and parallel. These are not geometric interpretations. Back when we were doing the light bulbs one, if we took one of the light bulbs out when they were in series or opened up the switch, they both went out. Would that happen here? If I were to take this resistor completely out of the circuit, would this one go out or would this one stop working? You bet it would. And that's a great way to tell if resistors are in series. If you take one out and the other one stops working, they're in series. They depend on each other. Another way to think about it is if you were to track an individual proton through the circuit, what happens? Well, here's our battery. Again, the long line is the positive terminal. We have all our protons held up against their will with their potential energy stored there. And so a proton comes out of the positive terminal. Wait for my cursor to show up here. And it's going to come out of the positive terminal. It's going to travel through the first resistor up top here. And then after traveling through this first resistor, where must it go next before heading back to the battery? It's got to go through another resistor and then completes the circuit. So here's a great way of telling if things are in series. If it goes through one, and then if it has to go through another, that means they must be in series, which also goes along with the idea that if you take one out, the other one stops working, they depend on each other. Okay, so are any of these other circuits a pure series connection? And hopefully you would tell me letter D is a pure series connection. Even though there are 1, 2, 3, 4, 5, 6, 7 resistors, hopefully you see if you take any one of these resistors out, you've broken the circuit, all the other resistors will stop working. If they're light bulbs, they'll all go out, and that makes it a series connection. Or, if we start here at the positive terminal and watch one individual proton come out of here and go here, where does it have to go next? It has to go through this one. Has to go through there before coming back to the negative terminal and completing the circuit. And that's a great way of telling they are in a series connection. Now, just a quick disclaimer here. While I'm thinking about just one individual proton traveling through the circuit, in reality, remember, there's billions and billions, and it's not like they really start here at the positive terminal. They're all throughout here. They all are moving around together. It just really helps us to visualize one individual proton as we're imagining what it does and seeing whether it has to go through another resistor to tell if it's series or not. Okay, then in class I would ask, are any of these connections purely parallel? And usually the first one students say would be letter F. Well, let's see. So here we have charges coming out of here, and then, there is a place where the charges can separate, go down different branches of the circuit. And one way we saw in the light bulbs of telling they're in parallel was if you take one out, will the other one still work? So if I were to take this one out, will the other one still function? You bet. They all have their own individual complete circuits. If I take even 1, 2, 3, 4, 5 of these light bulbs out, will the sixth one still work? You bet. It doesn't have to be this one on the end. Any of them. They are all independent of each other. That's a great way of telling that they're in parallel. One other quick disclaimer here, I'm tracking the charge that comes out of the positive terminal, and then it has to get back to the negative terminal. So maybe we would go down this path and complete it, or this path, or this path. But a charge will not go down, let's say, this path, and then backtrack over here and go the other way through this, sort of crisscrossing and crossing the stream with other protons who are trying to get to the negative terminal. In these circuits that we're drawing here and we're studying, the charges only flow in one direction. We call these DC, or direct current circuits, meaning that the charges only flow in one direction, from the positive terminal going through some circuit element to then back to the negative terminal. They'll never cross paths, as we imagine what they're doing. Okay, are any of these other circuits purely parallel? And some of you may have said letter A. Let's take a look to see whether they're parallel. First thing I say is, wait a second, this resistor and this resistor are on what looks like perpendicular sets of wires. That can be parallel. Okay, but I go back to the idea that parallel is not a geometric interpretation. While we draw them this way, and sometimes on the PhET simulation we build the circuits this way, when you actually have wires and resistors and batteries, you don't really have to make these exact connections. They don't have to be straight lines, they have to be right angles. And so you're not going to necessarily have them parallel and parallel, as they were here in letter F. The real test is to see, if you take one out, will the other function? So if I take this resistor out, will this one still work? Well, yeah, it's got a complete path. If I take this one out, will this one still work? Sure, it's on its own independent branch. That's what makes them parallel, that they are independent of each other. Okay, so what about B or E? Is either one of them purely series or purely parallel? Let's take a look at letter B first. So let's watch an individual charge. An individual charge comes out of the positive terminal, goes to this resistor, great, and then it has this part of the circuit where there are these different branches. It's like, the charge is split up, that means it must be parallel. But let's watch what just happened, right? To get to either one of these resistors, this charge first had to go through this one. So if I take this one out, will these ones still work? Well, no, that would break the entire circuit. That sounds like series, doesn't it, right? The fact that if it goes through one, it has to go through another, or if I take one out, other ones stop working, sounds like series. But the fact that it can split up and go through either one of these sounds like parallel, right? If I take this one out, will this one still work? Well, yeah, as long as this one's there. So that sounds like compound. This is our first example of a combination of series and parallel. So we don't say this resistor is in series with this one or this one because of this part of the circuit where the charge is split up. We say that this resistor is in series with the combination of these two, or these two are in series with this one here. But it's got to be a joint effort there, right? If it goes to this one, it doesn't actually have to go through this one or go to this one. It has to go through one or the other, but not one individually is what I'm saying. Okay, how about letter E? All right, well, charges come out of here, and here, again, we got the different branches, top branch, bottom branch, which immediately makes you say, it must be parallel, because it seems like, there are choices to be made. But then if we watch an individual proton, when it gets to this one, let's say it goes to the top branch, and it goes through this resistor, where must it go next to get back to the negative terminal? It's got to go through this one. That sounds like series, right? And so here we have another example of compound. These two resistors are in series with each other. If I take this one out, this one fails. Take this one out, this one fails. These two resistors are in series with each other. Again, if I take one out, the other one fails. But the top and bottom branches are in parallel. So again, we have a combination of series and parallel, a compound circuit.